You turn on the tap in your cabin to brush your teeth. Water comes out. Of course it does. It always does. You don't think about it for even half a second. You probably should. The ship is somewhere in the middle of the Caribbean, or the Mediterranean, or the North Atlantic. The nearest city is hours away. There is no pipeline reaching out here, no water tower on the horizon, and a ship this size, 5,000 passengers and crew moving through it, showering in it, cooking with it, filling multiple pools with it every single day, burns through a volume of fresh water that would be difficult to even picture. You couldn't load that at the pier, not remotely. You'd need an armada of tanker trucks and a week you don't have. So where does it come from? The ship makes it every day while it moves, and the way it does that is one of the more quietly elegant pieces of engineering on a vessel that most people only ever experience from the pool deck. Follow it back. The water that came out of your tap traveled through a distribution network threaded through the hull the way plumbing runs through any large building. Pressurized supply lines, hot water loops, branch connections dropping off at every deck. Trace those lines downward and they lead into the freshwater storage tanks sitting low in the hull where the weight helps with stability. The tanks are segmented, not one giant reservoir, but multiple separate compartments, and the ship keeps them continuously topped up. Not days of reserve sitting idle, just a working buffer large enough to absorb a production hiccup without anyone on Deck 12 ever noticing anything off. The passengers are the last to know. That's the point. What fills the tanks is a different question entirely. The first method is evaporation, and the physics of it is almost comfortingly simple. Seawater gets drawn in from outside the hull and fed into a sealed, low-pressure chamber. Here's the key. When you reduce the pressure around water, the temperature at which it boils drops significantly. At low enough pressure, seawater will boil well below 100 degrees Celsius, far below what you'd need at the surface. The water turns to steam. The salt doesn't. Salt doesn't evaporate, so it stays behind as concentrated brine and gets discharged back overboard. The steam rises, contacts a cooler surface, condenses and drips down as pure, fresh water. Clean, reproducible physics. The hard question isn't how the evaporation works. The hard question is what's supplying the heat. You'd reasonably assume a dedicated energy source, a boiler, a heating element, some meaningful draw on fuel. A ship running evaporators continuously at sea must be burning something extra to keep them going. It seems like the obvious setup. The heat comes from the engines, not as a clever bonus feature, not as an engineering afterthought someone figured out later. The main propulsion engines, whether diesel or the LNG burning systems common on newer vessels, run extraordinarily hot, and managing that heat is one of the central challenges of operating them. The solution is a jacket cooling system, a continuous loop of water that circulates around the engine block, absorbs the heat it generates, and carries it away before it causes problems. On a basic vessel, that cooling loop passes through a heat exchanger and the ocean absorbs what it took away. Useful heat produced at continuous cost, discharged into the sea. On a cruise ship, that cooling loop gets routed through the evaporator first. The engine's waste heat the ship was generating anyway, heat it had to shed regardless, becomes the evaporator's primary energy source. No extra fuel burned, no separate boiler running alongside. The propulsion system and the water factory are not parallel operations. They are the same operation, doing two jobs simultaneously, with the second job costing almost nothing once the first one is already running. The engine room isn't just moving the ship, it's running the hotel above it. Most large modern ships run a second method alongside the evaporators, reverse osmosis, or RO. Where evaporation uses heat, RO uses pressure. Seawater gets pumped at very high pressure through semi-permeable membranes, a filtration material so fine that water molecules pass through under force, but salt ions are physically too large to follow. Fresh water exits one side, concentrated brine exits the other and goes back overboard. RO doesn't depend on engine waste heat. It needs electrical power and precise membrane maintenance. Most modern large ships run both systems, evaporation as the workhorse, RO as the complement or backup. But here's where it gets interesting. Both methods, evaporation and reverse osmosis, produce water that's almost too pure. Strip everything out of seawater and what you're left with is something demineralized, flat, mildly aggressive to metal piping, and slightly hard on the body over extended consumption. Completely clean. Not quite right. Pure water isn't finished water. Before the fresh water enters the distribution system, it passes through a treatment stage where minerals are added back in, calcium carbonate, magnesium, in controlled doses calibrated to the ship's specific standards. Chlorine goes in for microbial control, pH gets adjusted. What comes out of your tap isn't raw desalinated seawater, and it isn't just purified water either. It's a formulated product. Ocean water reduced to almost nothing, then carefully rebuilt to specification. The ship isn't merely making water, it's engineering it. A large modern cruise ship might produce somewhere between 500 and 1,000 metric tons of fresh water in a single day. Verify against current ship class specifications before recording, as figures vary significantly by vessel. Across a 7-day Caribbean voyage, that's roughly the equivalent of filling 2 to 3 Olympic swimming pools with water made entirely from the ocean the ship is sitting on. Every shower, every pool, every gallon of stock in the galley, every ice cube and every glass at every bar on every deck, all of it started as seawater coming in through the hull. Which raises the question most people get to at some point. Is that actually safe to drink? The answer is yes, and the infrastructure behind it is more rigorous than most passengers realize. Ships calling on U.S. ports operate under the oversight of the CDC's Vessel Sanitation Program, the VSP, a regulatory body that inspects water systems, food handling, sanitation conditions, and more. VSP scores are public record, posted on the CDC's website and searchable by ship name. The same basic concept as a restaurant health inspection, except most passengers have never thought to look their ship up before boarding. Beyond VSP, the ship's own crew tests water independently and continuously at the point of production, in the storage tanks, at distribution points throughout the ship, and at the top, multiple times per day. Shipboard water consistently meets or exceeds the standards of a municipal system on shore. The bottled water in your cabin's minibar is a preference, it is not a precaution. Now here's where most people assume the obvious fallback kicks in. Fine, but if something goes wrong with production, the ship just loads up on fresh water in port, right? Top off the tanks at the pier and carry on. It seems like the natural contingency. Most passengers picture the ship topping up on water at port the way a road tripper fills up at a gas station. The ship is the gas station. Port water costs more per metric ton than producing it on board, sometimes significantly more depending on the port. Quality varies. What meets acceptable standards at one Caribbean harbor may be marginal at the next, and the ship would need to independently verify every load before distributing it through a system that supplies drinking water to 5,000 people. Then there's the logistics reality. The volumes required on a large modern ship are substantial, and loading fresh water at the pier competes directly with the turnaround window that's already packed with passenger embarkation, provisions loading, fuel transfer, and waste offloading. That window is tight. Loading water loses that competition almost every time. The onboard production system isn't the nice-to-have that port water backs up. It's the primary supply logic for every voyage. Port water is the contingency for the contingency. Which is also why the system is built with redundancy designed in from the beginning. Multiple evaporator units run alongside RO. The storage tanks carry working buffer capacity. If one evaporator needs to come offline for maintenance or repairs, the others keep running. If production dips for any reason, the tanks absorb it. A single component failure doesn't create a water emergency. The engineering assumes component failure will occur and accommodates it without the passengers noticing. The same philosophy that puts backup generators and redundant power systems on a cruise ship runs all the way through the water infrastructure. The failure mode was considered before the vessel left the shipyard. Production runs continuously while the ship is at sea. The evaporators are most efficient at cruise speed when the main engines are running at full load and generating the most waste heat to capture. But there's a second reason production has to slow near port, and it has nothing to do with engine load. Coastal seawater carries bacterial contamination that open ocean water doesn't, so the evaporators must shut down entirely within roughly 4 nautical miles of shore. Both factors push in the same direction. The buffer tanks absorb the gap either way. It's a continuous cycle tuned to the ship's operating rhythm, not a fill once and drain sequence. This system is also, quietly, what makes the hospitality product possible. Unlimited showers on a ship with 5,000 people, pools on multiple decks, spa hydrotherapy pools, continuous galley operations. None of that survives the economics if the ship is purchasing water by the ton at every port call, at port prices, against a clock that's already running. The water factory, running primarily on heat the engines were generating and discarding anyway, is the infrastructure that underwrites the luxury promise. You can offer an unlimited shower because the ocean below you is also the source. Every major cruise ship works this way, has for decades. The passenger turns on the top, the water runs, and somewhere below the waterline, the evaporators are cycling, the membranes are filtering, the mineral dosing system is rebuilding with the process stripped out, completely invisible, completely routine, completely irrelevant to the person rinsing their toothbrush in cabin 8142. Next time you feel the engines through the deck, that low, steady vibration that means the ship is underway, there's a reasonable chance they're making your drinking water at the same moment they're moving you across the ocean. 2 jobs, 1 machine. That top in your cabin isn't a connection to shore, it's the last stop in a production chain that starts with the water outside the hull, and it was already running long before you boarded. That's another one for the cruise files. If you want to learn more about what goes on behind the giant cruise ships, everything from the scams on board to the secrets below deck, subscribe, like, and share. Thanks for watching, and I'll see you in the next one.